Hello students, welcome to today's class. Hope you people are well. So today's topic is complex numbers. Previously, you have studied about quadratic equations and how to solve them. Let's take an example. X square plus 1 is equals to 0. Let's solve this quadratic equation using basic mathematics. I can write it as x square is equals to minus 1 and x is equals to plus minus root under of minus 1. Now I am stuck here because from the previous knowledge of real number system, I know that the square of any real number is either positive or 0. That is, for all a belongs to R, my a square is greater than equal to 0. But in order to find the root of this quadratic equation, I need to find the square root of a negative quantity. Now, anyone would feel stuck here and say this quadratic equation doesn't have any solution. But we mathematicians are very solution oriented people. We say, let if possible, this quadratic equation has a solution. Now, how does that solution look like? Let us denote root under minus 1 is equals to iota. Now you might call it iota or I based upon your convenience. For the rest of the lecture we will be calling it I. So substituting it over here, we have x equals to plus minus I, which is the required root of this quadratic equation. Now you might have a question in your mind that for finding the square root of minus 1 I have used this notation. But if it were any other negative quantity in place of minus 1, should we have used a different notation? If so, you know that there are infinitely many negative real numbers. So for every negative real number, if I use a different notation, doesn't it sound a little bit impractical? So let's tackle this question using another example. Suppose 2x square plus 3x plus 4 is equals to 0. Then by using Sridharacharya's formula, I can write x equals to minus b, that is minus 3, plus minus root under of b square, that is 3 square is equals to 9, minus 4ac, that is 4 times 2 times 4, that is 32, divided by 2a, that is 2 into 2 is equals to 4. That equals to minus 3 plus minus root under of 9 minus 32 is minus 23 divided by 4. Now observe, minus 23 can be written as minus 1 into 23, right? Taking square roots both sides, I have minus 23 is equals to root under of minus 1 into 23. That can be written as root under of minus 1 into root under of 23. And this we have denoted as I. So this equals to I times root under 23, right? So substituting it over here, I have x equals to minus 3 plus minus root under 23i divided by 4, which is the required root of this quadratic equation. So from here we observe a thing that by using just this notation we can find the square root of any negative real number. Okay, now let's move on to the definition of complex numbers. Definition: any number of the form a plus ib is called as complex numbers where a and b comes from a real number. Now observe that these quantities have two components in them. First is a real number and second is the coefficient of I. So this part of the complex number, this real part of the complex number is called as the real part of complex number. Now let us denote this complex number as Z. Then this real part of the complex number Z would be denoted as this Re of Z, that is real part of Z. And then this part, which is the coefficient of I, is called as the imaginary part of the complex number Z, which will be denoted as Im of Z. Okay, now let's take few examples to understand this well. Example, if Z is equals to 1 plus 2I, then here the real part is 1, so real part of Z is equals to 1, and imaginary part of Z is the coefficient of the I term, which is 2, so imaginary part of Z is equals to 2. Now when I identify these quantities as numbers, I now have a question that whatever numbers we have seen previously, may it be natural numbers, integers or real numbers, they had some properties. They could be operated together with some operations like addition, subtraction, multiplication and division. Now my question is, can I operate these quantities too? So let's start with addition. Let Z1 is equals to A plus IB and Z2 is equals to C plus ID. Now A plus IB plus C plus ID. Now first writing the real parts together, that is equals to A plus C. Now observe these two terms have I common between them. So taking I common, I have I times B plus D. That I can write it as A plus C plus I times B plus D. So from here we see that while the addition of two complex numbers is the sum of its real parts plus I times the sum of its imaginary parts. Okay, let's take an example. 1 plus 2I plus 3 plus 4I is equals to sum of the real parts, that is 1 plus 3, which is 4, plus I times sum of the imaginary parts, that is 2 plus 4 is equals to 6, 6 times I. So the sum would be 4 plus 6I. Again, the sum of two complex numbers comes out to be a complex number. Similarly, we can also show that the subtraction, multiplication and the division of two complex numbers is always a complex numbers. Now, let's see how can we plot these complex numbers in graph. Previously, you know that any ordered pair AB in R2 corresponds to a point AB in the XY plane. Say this is my XY plane, say this be my point AB. Now, complex numbers can't be plotted in the XY plane. For complex numbers, we need a different plane called as the Argand plane. Now, the Argand plane consists of two perpendicular axes. First is the vertical axis, which denotes the imaginary part of a complex number, and the next is the horizontal axis, which denotes the real part of a complex number. Now how do we plot complex numbers in that plane? Suppose Z is equals to 2 plus I, then the real part of Z is 2. So let's take 2 units here. Suppose this be my 2. And the imaginary part of the complex number Z is 1. So take 1 units over here. So my complex number would be somewhere here. This would be 2 plus I. Right? Now you might have a question that these two planes, they look somewhat similar. So why do we even need to study this plane? Why can't we plot the complex numbers in the XY plane itself? The answer is, in the XY plane when we plot a point, we plot the values of two variables. But in the Argand plane, when we plot a point, we plot the values of two components of a single complex number. That is, every single point on the Argand plane corresponds to a unique complex numbers, which enables us to visualize operations like addition, modulus, argument and rotation geometrically, which we can't do in the xy plane. Okay. Now, let's move on to the next topic, modulus of a complex number. Modulus. Modulus of a complex number z is equals to a plus ib. Let this be my point a plus ib. Then this point would be a, as my real part is a, and this would be my imaginary part b, and hence this distance would be b units, this would be b, and this distance would be a units. Okay. Now the modulus of a complex number z is equals to a plus ib is denoted as mod z and is defined as the distance between the complex number and the origin. So here this line represents the modulus of the complex number z. Okay. Now look, this triangle is a right angle triangle. So let's first name it. Let this triangle be named ABC, right? Okay. Now, in triangle ABC, if I use Pythagoras theorem, I have hypotenuse square is equals to perpendicular square plus base square, and the hypotenuse is mod z. So mod z square is equals to base square, that is AB square, and AB is a units, so a square plus the perpendicular square, that is b square. So this implies mod z is equals to root under of a square plus b square. So this is how you can calculate the modulus of any complex number. Example, if z is equals to 1 plus 2i, then modulus of z is equals to root under of 1 square plus 2 square. So this would be equal to 1 square, which is 1, and 2 square is 4. So 1 plus 4, 5. So it would be root 5. Okay. Moving on to next topic, argument of a complex number. Now argument of a complex number z is defined as the angle made by the line joining the origin and the complex number with the positive direction of the horizontal axis. So here this would be the argument of complex number, and argument is denoted as theta. So this is our theta. Okay. Now observe one thing, that this line, if we rotate this line for a full circle, still it would point to the complex number a plus ib. But now it would make an angle 2 pi plus theta with the positive horizontal axis. Okay. Now let's rotate it once again for a full circle. Still it would point to the a plus ib, but now it would make an angle 4 pi plus theta with the positive horizontal axis. That means that argument of a complex number is not a unique value, but for our calculations we need a steady value, we need a fixed value. So now let us define the principal argument of a complex number. The principal argument of a complex number is denoted as argz and is defined as the unique argument value of a complex number between minus pi to pi. Okay. Now in this lecture we will be focusing more on the first quadrant, and in the next lectures we will be studying about the argument of complex number in the second, third and fourth quadrant. So in the first quadrant, argument of the complex number will be theta. So argument of z is equals to theta. Now observe, in the triangle ABC, if I want to find a relation between theta A and B, if I take tan theta, then tan theta would be equals to perpendicular by base. Now my perpendicular is B units divided by my base is A units. So this implies theta is equals to tan inverse of B by A. So this is how we can find the principal argument of any complex number in the first quadrant. Let's take an example. If z is equals to 1 plus I, then the principal argument theta would be tan inverse of 1 divided by 1. That is equals to tan inverse of 1, which equals to 45 degree. Okay. Now let's move on to the topic conjugate of a complex number. Now conjugate of a complex number z is equals to a plus ib is denoted as z bar and is defined as a minus ib. Now as you can see here, while finding the conjugate of a complex number, the real part remains same but the sign of the imaginary part gets changed. Now let's plot it graphically. Now the real part of the conjugate of the complex number remains same, but the imaginary part is minus b units. So taking minus b units from the origin, I come to this point. So this would be my a minus ib. So as you can see from the graph, a minus ib is the reflection of the complex number a plus ib with respect to the horizontal axis. Okay. Now let us find its modulus. So modulus of z bar is equals to root under of a square plus minus b square, right? That would be equals to root under of a square plus b square. But previously we have seen that the modulus of complex number z is equals to ib is root under a square plus b square itself, right? So this means from here we have two observations. Number one, the modulus of a complex number and its conjugate is same, and number two, the two complex numbers having the same modulus need not be same. Okay, now let's move on to an important topic, polar form of a complex number. Now previously we had been representing z in terms of x and y, but in case of polar form we represent z in terms of r and theta, okay, where r is the modulus value of the complex number and theta is the principal argument of the complex number. Now, how do we do this? In the triangle ABC, observe, if I find sine theta, then sine theta would be equals to perpendicular by hypotenuse, and perpendicular is b units divided by hypotenuse is z, is r, right? So it would be b by r. This implies b equals to r sine theta, right? Again, if I take cos theta we know it's base by hypotenuse. Now base is a units divided by the hypotenuse, it's r. So a becomes r cos theta. Now previously our z was x plus iy. Now substituting the value of let us write it a plus ib. Now a is equals to r cos theta plus I times B is r sin theta. So r sin theta. That becomes r times cos theta plus I sin theta. And that becomes r e to the power I theta, where this e to the power I theta is equals to cos theta plus I sin theta. And this is the polar form representation of any complex number z with modulus r and principal argument theta. So this was all about the introduction of complex numbers. In the next classes, we will study about the principal argument of complex numbers in the second, third and fourth quadrant, and then the De Moivre's theorem. Thank you.